Artificial intelligence methods for Earth systems.
But yeah, anyway, I'll get started. So the paper I'm presenting today has the title Unsupervised Scalable Representation Learning for Multivariate Time Series. So, there's lots of stuff already packed in there by Franceschi et al. From, I think, 2019 or 20, was published at NeurIPS. And as the title already suggests, it's a paper about representation learning for time series and kind of their specific approach to this task. So I'll get started with just the general problem setting that's handled here, where the case that they look at in this paper is taking multivariate time series where different dimensions might have varying lengths even in time, and then find representations of these time series without using any label information. So you don't know, right, if you're thinking about a setting like a time series classification, you don't know the outcome of whatever this input time series might be. As I said, inputs can have varying lengths. This is one of the main points that they stress of novelty, kind of. And then they want this to be universally applicable to downstream tasks, which is kind of a bold claim, because lots of representation learning stuff really derives its representations from, or the usefulness of these representations from kind of the predefined downstream task, and then having some intermediate model find the representation that's most suited for this. And this paper kind of takes the opposing approach where they say, well, if you can just find they use the word universal representation for these one time series, then we might be able to apply this to whatever we want without specifying it beforehand. And so kind of visually what's going on, right, is that you have some time series that they call Y of observations that can have different lengths. And then you have whatever their model is. And then you arrive at some representations that still have some kind of length in time, but they're all the same length. So you have just kind of representation series that are all mapped to have equal lengths. And you have one of these kind of for each of your input observations. Exactly. And so the model that's used for this, I'll start with the objective and then kind of move on to the actual architecture that's used in practice. And the intuition behind this here is that if you don't define a task beforehand, right, you have to think about what kind of in your representation space you want your inputs to be mapped to. And so the intuition, I think, is fairly clear, and it's that things that are similar, right, without defining what similar means beforehand, things that are somehow similar should be also close in this learned representation space, and then things that are kind of dissimilar or have no connection should be far apart using some sort of distance metric. And so the way that this then is presented is using this so-called triplet loss function, where triplet just kind of refers to the inputs that you have to give this loss function, where the first of these triplets is, or the first component of this triplet is this kind of reference chunk, which is represented here in blue, which they call xref. So you kind of just take one sub-segment of your time series, which is your reference, and then you have a positive sample, which is usually sampled from within or in the direct neighborhood of this reference sample. So right, this green thing here, and this can be a sub-series that has a super small length or can be kind of longer. This is not specified to begin with. And then you have a negative sample, which is supposed to be the one that's unrelated. And so this is just randomly sampled from either, if your time series is super long, from kind of very far away in time of your reference, or just from an entirely different input in general. So you have this triplet consisting of your reference, your positive sample, and then your negative sample. And then the actual loss function takes this form, where the thing that I want to highlight is these two components, right? This first one, and then this second one. And starting with the first one, this is kind of the part of the loss function that's supposed to push your representations that are similar, right? So your reference and your positive sample to be close to each other. So F is essentially the embedding function. So whatever the function that maps from your objective to your representation space, from your observed space to your representation space. So this is something that you have to learn, right? And these parameters theta are just the parameters of your function that you're learning. And then the sigma here is the sigmoid function. And so you can kind of, if you take a super simple example and you write it down, you can convince yourself that this first term here pushes things that are kind of similar to be close together in this space. And then this second term here, we have the sum over k, and k just refers to the fact that in practice, you don't only take one negative sample, but you take k negative samples, just because this somehow proved to work a little bit better. And you see basically it looks exactly the same, other than the fact that you have this minus sign here. So you're trying to do exactly the opposite. And again, if you write it down, you'll be able to convince yourself that essentially this reference and then the embedding of the negative sample, this formulation of a loss function tries to push them further apart in this representation space. But I think the intuition is more important. And so using this loss function, or kind of the question that arises now, right, is how this f, right, this is kind of the meat of the method here, how this function is found, with which the authors claim to find these universal embeddings. So given a time series, how do I arrive at my representations? So that's kind of the second part of the model, right? Looking at the architecture. And I would say that this is actually the main contribution of this paper. There's not really a theory part, so it's really kind of introducing a novel way of learning this embedding function. And because of this kind of universality claim, they don't use something like a VAE, like a variational autoencoder architecture, if that's something that you're familiar with. But they kind of only use an encoder and then have this embedding in this representation space, and that's where they compute their loss. And so the way that they implement this encoder is by using so-called dilated convolutions. So just kind of one-dimensional convolutions in time, and dilated refers to the fact that your kind of sliding window doesn't necessarily always take adjacent inputs, but you can kind of skip some of them, right? These are supposed to be represented by the fact that these red lines show what you have to use as an input to get one of these output cells here. You can see that you can skip some of the preceding input series. And these dilated convolutions, they have kind of two, I would say, nice properties that you can exploit. So first of all, that the fact that they're convolutions means that you can parallelize this in practice. You can let this run on GPU, and you can have kind of a significant speed up if you're dealing with high dimensional data, as opposed to having some kind of sequential model, right, where you really have to feed in kind of step by step, something that you just can't parallelize. And then the fact that they're dilated, this just leads to you having a larger receptive field. So, right, receptive field for convolutions just means for one output, kind of how much of an input do you span, right? Like visually, how much of this input series is captured by one of these outputs. And if you have dilated convolutions, you can expand your receptive field with less layers, right? It's just kind of, it grows exponentially in the layers. So those are kind of the two arguments brought forth in practice of why you actually use this.
Just,
and then, yes.
Yeah. Whenever you, yeah. So there was just one small question. I see from the figure in this dilated causal convolutions. Is it also always true, like for any cell in the upper layers, we only use values before that and not after that? Yes,
exactly. I mean, this is kind of, yeah, exactly. They're called dilated causal convolutions. And this, yeah, it already says it down here, right? And causal in this sense refers to kind of the signal processing understanding of causal, which just means that for some output entity, you only use values from the current time step or the past, right? And so in practice, this is also enforced, right? That you wouldn't use anything that somehow precedes in time step this output. And it's I would say kind of an argument that's not used in practice, but it's implemented because then you can kind of use this in an online fashion, right? If you get new data, then you can just kind of update this in one step with using your past inputs, and you don't have to rely on anything in the future. So you could actually use this somehow in practice if you're only measuring things, right? And you don't know what's going on in the future yet. Yeah. Exactly. And so these dilated convolutions, so one of the layers of this model, right, that you can then stack together to build your full model of your encoder, looks like this, where you basically have two of these dilated convolution blocks, and then kind of your dilation increases with each layer, right? So you kind of expand, 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 expand. Right, this is just kind of supposed to be a schematic overview. I think the details of these choices of how the layer is built are usually kind of more informed by practical reasons than some theory. And then at the end of these layers, right, so you can just stack them. And then the final layer is this max pooling operation, which then kind of in practice enforces the fact that if you have different inputs or inputs of different length, that this max pooling layer forces them all to have some predefined length. So you set, I don't know, your length of your representations to something like 10, maybe 10 time steps. And then this max pooling layer can deal with the fact that for inputs of varying length, it maps it to something that has length 10. So this kind of mapping from arbitrary lengths to something that you defined is really happening in this one building block.
So just to clarify on that, suppose we have say a time series of length 100 and the other of say length 1000. It just the max pooling is done in a way that it just forces both of them to be of a given size, say 10.
Exactly. So the way that I understand it, I didn't look at the code, but the way that I understand it from the description is that in your max pooling layer, you can define, right, if you have, I don't know, length 10, that you want the 10 largest values.
Okay.
And you take the, exactly. That's kind of what's done in practice. So it's a kind of a very ad hoc approach. But yeah. And so if there's no more questions, I'll move on to the results part of their paper, which I think is really also the part they spend the most time on, because there's, as I said, there's no theoretical founding so much. So they kind of rely on very extensive results to make the argument of why this is useful and why we should care about this. And so the setting of what's going on is that they use their model to learn some sort of embedding of time series, right? Some representations. And then using these representations, they perform some classification tasks. And so there's these benchmark data sets for time series classification. And essentially they make the argument that if you use this thing as kind of a pre-processing, right? You take your inputs, you learn the representations, and then you take the representations to actually do the classifying, that then this provides some kind of benefit. And so they compare against the whole broad state-of-the-art kind of spectrum of time series classifiers for supervised settings, unsupervised settings. And so using these, they have a bunch of different setups, and I'm going to go through all of them and kind of summarize the arguments that they make. So the first one is that they use univariate time series. So they don't actually use the multivariate capabilities of their model. And then they show that they outperform unsupervised classification models, and they come close to supervised classification models, which is right nice somehow. It's a result that's fine. And then they have another setting where they use so-called sparse labeling. So the setup is kind of, you have a huge data set and you only have labels for a small fraction of your samples. And then they say, well, we can use our model to learn these representations. And then given these representations, we can still use the few labels that we have on the representations. And somehow these labels become, or these labeled samples become more informative because of the representation that we've learned. And they show that this is in fact the case, that somehow pre-processing with their representation learning algorithm provides benefits compared to other approaches that have to that only rely on the very few labels that they have in a supervised setting. So that's the claim that's made here. Then
just one moment for the sparse labeling part. You do mention, like, is it something like we learn the representation of these time series, and then based on this representation, we train the model?
Yeah.
This is said. No, okay.
Exactly. Yeah.
Okay.
And then there's another setting where they do non-parametric classification. And this is essentially just unsupervised classification. And they show that their representation somehow, because of this loss function that they employ, naturally does some kind of clustering operations. And so if you kind of only employ this thing that doesn't have, like, isn't specifically defined as a classifier, you can somehow still show that like distances in the latent space have some sort of semantic meaning, perhaps. I mean, this is an experiment that I didn't really see the point of them including, but it's there. And then there's one thing, an experiment that they call transferability, where essentially they say they train a representation, or they train their model on one data set, and then they use the trained model to learn representations of another data set, and that then their classifier is still somehow meaningful, and they still get good results using their downstream classifier. And so this is where their big universality claim somehow comes in, and they say, well, because even if on totally unseen data sets, our representation is meaningful, where meaningful means we get a decent classification score. That's what's done there. And then they finally come to the multivariate time series setting, where they show that their classification also works, but they don't compare to any other baselines, because they say, okay, there's no multivariate time series classification benchmarks or something like this. And it's one experiment where they show that the classifier is somehow better than guessing. And then finally, they also do with long time series, because this is something that they also say is nice about their approach, because it's fast and it's scalable. And you use convolutions that they take time series that have length, like I think order of magnitude in the millions or something, like 2 million time steps. And they essentially show that if you take these super long time series and then you learn representations on them, that then you gain some sort of marginal speed up, as opposed to not doing this if you were to do some sort of classification task on them. Yeah, that's the experimental section. But now to the more, I would say, fun part, the discussion about this. So I just very broadly classified it into some of the strengths I think the paper has, and then some of the weaknesses. And so I think it's interesting, at least, to have this kind of novel perspective on this task agnostic representation learning, because this is something that really, at least in the representation learning literature, is not at all touched upon a lot, because I think, at least in practice, somehow it's proven that machine learning models that are highly successful and have some sort of representation learning baked into them, like large language models, or I don't know, something like ImageNet classifiers, right, where you can say, okay, one of the intermediate layers is a representation. They're super specific to a certain task, and you can't just transfer them to something else. And so kind of, at least empirically and also theoretically, there would be no reason why to assume that kind of this task agnostic perspective is the way forward, but they at least explore it, which I think is worth stating. Their architecture does provide useful representations for these classification tasks. That can't be, right, there's no argument against that. But I think, at least in my perspective, there might be a bit more weaknesses, or some of the weaknesses were maybe more pronounced to me, or something to talk about, at least. So yeah, as I said, there's no actual theoretical foundation, which I think is always hard, right? If you have a paper that's going very specifically into these deep learning topics, I think the theory is not super established, but at least somehow you can try to make a connection, which just for me personally would have been nice somehow. And then I think the experimental results are kind of ambiguous. I mean, I think the claims that are made, this is also a point that I have here, are, in my opinion at least, a little bit overly ambitious for what's actually going on. Like this universality claim from this transferability experiment, I think it just kind of shows that, well, your classifiers somehow can deal with whatever representations come out of your pre-trained model, but I don't see directly why you could make the claim that somehow training on one data set gives you the correct, whatever that means, representation on another data set, and that also everything is only surrounding this classification task. I don't think that it's a proxy kind of for everything that a representation can aspire to be, right? There's no claims about interpretability of whatever these representations are, and never actually look at the representations. They're just kind of an intermediate step to some downstream task. Yeah, and so I think the experiments are kind of overselling it maybe a touch, but I see I'm already a little bit over time of my section, and I'd love to hear your thoughts or any of your questions, and also kind of thinking about, right, if from your perspective, if you're dealing with climate data or problems that are somehow within this domain, if you think this might be something worth looking at, and why or why not. So yeah, anyway, thanks for your attention so far.
Yeah.